We rely on liquid and glass thermometers every day to tell us if we need a winter coat or if we're running a fever. To make early instruments work, makers needed fixed reference points, typically the temperatures where pure water freezes and boils under standard pressure. But there is a physical catch. Different liquids, like mercury or alcohol, expand at slightly different rates. If you use different liquids to measure temperatures far above or below those fixed water points, the thermometers will actually disagree with each other. Because every liquid expands according to its own quirky rules, an absolute reference for expansion just was not available in liquid form. Scientists realized they had to look for a different kind of substance to get a truly objective measurement. To measure the true temperature of the universe objectively, physicists abandoned liquids entirely and turned to the highly uniform properties of gases. The solution they found was a device called the constant volume gas thermometer. Researchers made a remarkable observation. At low densities, it does not matter if you use hydrogen, oxygen, or nitrogen. Every single gas exhibits the exact same expansion behavior as it heats up or cools down. Because this behavior is completely uniform across different chemical elements, tracking a gas provides a mathematically perfect way to measure temperature. Gas provides the precise physical baseline that reveals how thermal energy actually works in the universe. Gas behavior relies on pressure, volume, and temperature. Hold temperature constant and shrinking volume increases pressure, Boyle's law. Hold pressure constant and cooling gas shrinks volume, Charles' law. These combine into the ideal gas equation, PV equals mu RT. This equation proves that the properties of a gas are perfectly locked together by math, leaving absolutely no room for the arbitrary inaccuracies of a liquid thermometer. We can apply that ideal gas equation directly back to the constant volume gas thermometer we looked at earlier. By designing the instrument to mechanically lock the volume of the gas so it cannot change, the math simplifies drastically. With the volume frozen in place, pressure becomes directly proportional to temperature. To find out how hot or cold the gas is, you just read its pressure. This gives physicists a flawless measurement system. As the thermal energy of the gas drops, its pressure drops along a perfectly straight, predictable line. If gas pressure drops in a straight line as it cools, what happens if we follow that line all the way to the bottom? This chart plots pressure on the vertical axis against temperature on the horizontal axis. As the gas cools, we watch the data line slope steadily downwards. We eventually hit a physical roadblock. We cannot measure this indefinitely because real gases get so cooled they condense into liquids. Once they liquefy, the gas laws stop working. Physicists use a workaround called extrapolation. They continue drawing that straight dashed line past the liquefaction point, tracking where pressure theoretically hits zero. Extrapolating the lines for several different gases, every single one converges at exactly negative 273.15 degrees Celsius. This mathematical convergence point is absolute zero. It is the absolute minimum temperature theoretically possible for an ideal gas. Discovering an absolute minimum temperature creates a philosophical problem for the Celsius scale. Having a measurement system where zero is just the freezing point of water on Earth is completely arbitrary. A British scientist named Lord Kelvin recognized that true physics required a temperature scale starting at the universe's actual minimum limit. He proposed an absolute scale, setting the foundational zero point exactly at absolute zero, or negative 273.15 degrees Celsius. This diagram compares the two systems. The conversion equation is T equals the Celsius temperature plus 273.15. The size of 1 unit in Kelvin is exactly the same as 1 degree in Celsius, only the starting line has been moved. The Kelvin scale serves as the natural scale of matter. By using Kelvin, zero truly means zero, the precise theoretical point where all molecular activity and ideal gas pressure cease to exist.